Heat is all around us. We feel it from the sun, when we cook, or even when we walk barefoot on hot pavement. But heat doesn't just sit still, it moves. Understanding how heat transfer is crucial in engineering, environmental science, and even how we stay comfortable in our homes. Today, we'll explore how heat moves and how we can measure and control that movement. What is heat? Heat is a form of energy. It flows from a warmer object to a cooler one. For example, when you touch a hot mat, heat travels from the mat to your hand. This transfer continues until both are the same temperature. Heat is driven by temperature difference, and it always flows from hot to cold. What is heat transfer? Heat transfer is the movement of thermal energy from one place to another. It's all about that temperature difference, whether it's heating a house in the winter or cooling your phone while it runs. Heat transfer is at work. And once the temperature are equal, heat transfer stops. This final state is called thermal equilibrium. There are three ways heat can move from one object to another. Each mode works in a unique way. First is conduction, where heat transferred through solids by direct contact. For example, a metal spoon heating up in a pot of hot soup, or an iron transferring heat to clothes while ironing. In convection, where heat is transferred in liquids or gases through the movement of particles. For example, a boiling water, where the hot water rises and cold water sinks, or a warm air circulating from an electric fan heater. Third and last is the radiation. It is where heat transfers through electromagnetic waves, and it doesn't need any material to travel. For example, feeling warm from the sun or a heat from a campfire reaching your face from across the fire pit. What do they have in common? All the three modes involve the movements of thermal energy from a region of higher temperature to a region of lower temperature. No matter how the energy moves, whether through a solid, a liquid, a gas, or even empty space, the goal is always the same: to reach thermal balance or equilibrium. They're all also essential in real-world systems like cooking, climate control, and power generation. How are they different? First is their medium of transfer. Conduction happens mainly in solids, where particles are tightly packed and touch each other. Convection happens in liquids and gases, where particles move freely and carry heat with them. Radiation happens through empty space, and it doesn't need any material at all. They also differ in the movement of matter. In conduction, the material stays still while heat moves through. In convection, the fluid itself moves, carrying heat along. In radiation, heat travels as waves, not using particles at all. They differ also in speed of transfer. Radiation can happen at the speed of light, which makes it the fastest. Convection and conduction are slower and depend on the materials, properties, and conditions. So, although they all move energy, the way they do it and where they do it makes each mode special. That's why engineers choose materials and methods carefully based on how heat is moving in a system.
What is conduction? Conduction is the transfer of heat through solids. When one part of a solid gets hot, its atoms start to vibrate faster. These vibrations pass energy to neighboring atoms like a game of energetic tug. Metals are excellent conductors because their electrons move easily, spreading heat fast. That's why pots are metal but handles are plastic or wood, which don't conduct well. One-dimensional steady-state conduction. In many designs, we only care about heat moving in one direction, for example, straight through a wall. This is one-dimensional conduction. If the temperatures along the wall don't change over time, we call it steady state. Heat keeps flowing, but the temperature at any point stays stable. These models helps engineers predict how fast heat moves through building walls, insulation, and machine parts. To measure how much heat is moving, we use this equation. Ka, close and open parenthesis, T1 minus T2 divided by L, where Q Q is equal to heat transfer rate in watts. K is equal thermal conductivity of the material, how easily heat passes through. Also, A is equal area of the surface, and T1 minus T2 equals temperature difference across the wall, and L is equal thickness of the wall. A material with high conductivity, a larger area, and a bigger temperature difference allows more heat to flow. A thicker wall slows it down. Let's try solving a real-life example using the heat conduction formula. Suppose we have a flat concrete wall that's 10 centimeters thick, which is the same as 0.1 meters. The wall's area is 2 square meters and it's made of a material with a thermal conductivity of 0.5 watts per meter per degrees Celsius. One side of the wall is at 40 degrees Celsius and the other side is cooler at 20 degrees Celsius. Our goal is to find out how much heat flows through the wall per second. Now, let's substitute the values into the formula. Q is equal to 0.5 times 2 times 40 minus 20, then divided by to 0.1. We start by calculating the temperature difference. 40 minus 20 is equal to 20. Now, we multiply 0.5 times 2 is equal to 1 times 20 is equal to 20. So the numerator is 20. Next, we divide by the thickness of the wall. 20 divided by 0.1 is equal to 200. The final answer is Q is equal to 200 watts. This means 200 watts of heat energy flow through the wall is every second due to the temperature difference. In other words, that's how much heat escapes or enters per second, depending on which side is hotter. This simple calculation helps us estimate energy loss and design better insulations for home, buildings, and machines. Here's what we've learned today. Heat flows from hot to cold. There are 3 modes: conduction, convection, and radiation. Conductions happen through solids. In one-dimensional steady-state conduction, heat flows straight through a material at a constant rate. We can calculate this using the heat conduction equation.
In conclusion, even though we can see heat, it's always active, moving from the sun to the earth, from machines to air, and from our bodies to our surroundings. By learning how it flows, we gain control. We can conserve energy, protect devices, and stay comfortable. So next time you feel warm, ask yourself, how is the heat getting to me? Chances are, it's through one of the modes we've learned today.